What is the physical significance of first order correction? Very, very important one. Okay, what is the physical signification? So we discussed just now, it is equal to 0. There is no first order correction. There is no linear Stark effect. So there is no linear star effect means the expression value of the Hamiltonian, perturbing Hamiltonian is equal to 0. And H equals minus P dot F. Okay, H equals minus P dot F. So we have already discussed H equals minus P dot F earlier. Okay, with the help of some interaction energy. So this energy. So minus P dot F, which is equal to 0. It says that either this term equal to 0 or this term equal to 0, because answer is 0. F cannot be equal to 0 because already you have applied the electric field. F cannot be equal to 0. Only way is your P can be equal to 0. If P equal to 0, it implies that there is no dipole moment for the ground state. If P equal to 0, it implies that the ground state of hydrogen atom doesn't have permanent dipole moment. There is no permanent dipole moment. It's a very, very important conclusion. Okay, for the hydrogen atom in the ground state, there will be no permanent dipole moment. Is it okay? The ground state wave function has a definite parity. Just now we looked into it as an odd parity. Suppose the wave function has an odd parity or wave function has an even parity. It implies that it has a definite parity. Definite parity means either odd or even. And we just now looked into this is an odd parity. And final answer is odd parity, correct? The integration of odd parity is 0. But final answer is odd parity. So it has a definite parity. But there is no dipole, permanent dipole moment. Suppose if you go for more than one electron, just leave the hydrogen atom alone. If you choose lithium or some other one, helium or lithium, okay, more than one electron, then this point will work out. The spacing between this point. Okay, that means that this will have a permanent dipole moment, but this will not have a definite parity. I repeat, for the hydrogen atom, we have a single hydrogen-like atom or hydrogen atom. We have a no permanent dipole moment, but there is a definite parity. Suppose if the system consists of more than one electron, that will have permanent dipole moment and that will not have definite parity. Just the opposite in nature. Is it okay? So that's the main conclusion. So there is no linear Stark effect in the ground state of hydrogen atom and hydrogenic system, hydrogen-like system. That is outermost electron will be only one. Outermost orbit will have single electron, like hydrogen. So that's what we call this as hydrogenic system or hydrogen-like system. For other atoms, the spacing between the sublevels increase linearly with the applied field for other atoms. So this will work out only for the hydrogenic system. If it is so, then this will have a permanent dipole moment and this will not have a definite parity. So this is the main conclusion. Okay. Now we'll go for the second order correction. Because first order correction just now we said it is 0. No other way, we'll have to go only with the second order correction energy. So which is nothing but quadratic Stark effect. Okay, this is second term. Can you remember? AF plus BF squared plus CF cube. This is the second order one. So second order in the sense we'll have to go only with the excited state. So n equals 2. If n equals 2, L equals 0 and 1. N minus 1. So 0 and 1. And what would your m? M will be minus L to plus L through 0. So minus L to plus L. So plus 1, 0, minus 1. Now we are going to combination of labels, NLM. We are going to combination of wave functions. So NM will be 2, just 2, 0, 0. This is one combination. Then another will be, 2 will be there always. Okay. Then another combination will be 2, 1, okay, 2, 1, 0. Then another combination will be 2, 1, 1. Another combination will be 2, 1, minus 1. So there will be 4 combinations. 2, 0, 0, 2, 1, 0, 2, 1, 1, 2, 1, minus 1. So there are 4 wave functions. 4-fold degeneracy. 4 wave functions. So 4-fold degeneracy. Yesterday we discussed about 2-fold degeneracy. So there will be 2 wave equations. Correct? 2 equations. 2 simultaneous equations. 2 secular equations. Correct? So similarly we will have here 4-fold degeneracy. So we can't use a non-degenerate theory. We'll have to use only degenerate theory. The continuation is correct. Okay, yesterday we are discussing about degenerate theory. So we have some equations and we could solve using matrix. Okay, so similarly we are going to use now degenerate perturbation theory. So degenerate perturbation theory occurs only we are going to diagonalize the matrix perturbic Hamiltonian in degenerate subspace. So similar argument will be for the excited state. For n equals to you love the answer will be minus 13 points divided by 4 minus 3.4 electron volt for all the 4 combinations. You are going to have all the 4 wave equations. What are the energy? Same energy, degeneracy, 4-fold degeneracy. Is it okay? So we'll have to go only with 4 by 4 matrix. So we'll have 16 elements will be there. We'll have to solve for 16 elements. Okay, in a matrix. Yesterday we solved for 2. So 2 matrix, correct? 2 by 2. So now we are going to have, since 4 wave vectors are there, we are going to have 4 by 4 matrix. So 16 elements we are going to solve. We need not solve 16 elements. Using parity method, we are going to solve only one element. Okay, that is the idea. That's the beauty of parity. That's the beauty of parity. So immediately we will come to know the answer if we know the parity well. Okay, we need not solve all the 16 components, 16 elements. Okay. Now, so these are all 16 elements now. Okay, so this is the secular wave equations. Can you remember simultaneous wave equation, simultaneous equations? Okay, these are all simultaneous equations. H11, H12, H13, H14. Similarly, H11, H21, H31, H41. And A1, A2, A3, A4, they are all constants. Okay. Yesterday we could have 2 equations, 2-fold degeneracy. Here it is 4-fold degeneracy. So 4 equations, simultaneous equations. So in a matrix form we can write these equations exactly as like this in a matrix form. So you have H11, 1, 2, 1, 3, 1, 4 term, and here it will be 1, 1, 2, 1, 3, 1, 4, 1. All diagonal terms will be H11, H22, H33, H44. And your constant, these constants will be as column vector and right hand side will be 0, 0, 0. Okay. So we are going to diagonalize now. So this will be your secular, we are going to take the secular determinant. So taking the determinant of this one, that will be equal to 0. Okay, very simple one. Now, these are all 4 combinations, a linear combination of 4 equations, correct? So they have kept us under ket vectors. Similarly, you can go for bra vectors, correct? So if you are going to keep it as bra vectors, sandwiched between your Hamiltonian, that will give us matrix elements. So 16 matrix elements are there. Okay. Now how to write this one? So just take the bra vector of this. So bra vector of this 2, 0, 0. The combination will be, see here, combination will be very simple: 1, 1, 1, 2, 1, 3, 1, 4 for the row vectors. First row vector. See here 1, 1, 1, 2, 1, 3, 1, 4. The combination will be like this. And for the column vector, this will be 1, 1, 2, 1, 3, 1, 4, 1 for the column vectors. Diagonal elements 1, 1, 1, 2, 2, 1, 1, 2, 2, 3, 3, 4, 4. Very simple one. Okay. Is it okay? How to write in terms of matrix. Now, this matrix element sandwiched between these two. Okay. Similarly, this matrix sandwiched between these two. Okay. So we have 1 here. 1 means bra 2, 0, 0. See everywhere bra 2, 0, 0. 1, 1. Then second one implies that 2, 1, 0. See 2, 1, 0. Then third one will be 2, 1, 1. Fourth one will be 2, 1, minus 1. So come on, any doubt? Writing in the matrix form. Now we are going to apply just 2 rules and get the results immediately. Well, just 2 rules. The first rule says that the same parity will become always 0. The same parity. If Hamiltonian, perturbic Hamiltonian consists of same parity. For example, H11, H22, H33, H44, all will become 0. So immediately we can get En2 minus En2, En2, En2. Because this one will become 0, this will be 0, this will be 0, that will also become 0. The first point. And second point, we discussed earlier about this symmetry operators in the last unit. Any symmetry operator operates on H that will have commuting variables which is equal to 0 while deriving the equation for motion. So both the operators are commuting with each other. That means they have simultaneous eigenstates which is equal to 0. Okay, so this can be written in terms of expansion. A comma B equals AB minus BA. So we can write this as exactly like this, sandwiched between your corresponding eigenstates, corresponding states. So M prime and M. Now Lz operates on M prime is given by this equation. Lz operates on M, that will give you M is the eigenvalue, so M H cross. M H cross, M stands for magnetic quantum number. H stands for, we know, reduced Planck constant. M H cross totally, that will be eigenvalue. Okay, this is your eigenvalue of Lz. So here Lz operating on M prime, that will give you M prime H cross, correct? And similarly Lz operating on M will give you M H cross. So H cross you pull it out, that will give you M minus M prime with that factor, which is equal to 0. H cannot be equal to 0. This cannot be equal to 0. Only possibility is M minus M prime can be equal to 0. Okay. So if M equals M prime, M minus M prime equals 0, M equals M prime, so we will have some values. Wherever you find M equals M prime, you will have some values. If it is not equal to 0, the answer is 0. See here, 2 is N, correct? Next term is L. Next term will be M. You find where M equals M prime, and you just find out where M is not equal to M prime. You just find out. Suppose we consider the second one. Already we have done the diagonal elements. We will go for the second one. Just tell me whether M equals M prime or not. This is your M prime. See here, this is your N, L, M, and corresponding bra will be N prime, L prime, M prime. This is N, L, M. Corresponding bra will be N prime, L prime, M prime. NLM, then this is N prime, L prime, M prime. Okay. Now just find out M equals M prime. This is your M prime. This is your M. So both are equal. Both are equal means it has some values. Non-zero matrix element. Here you just consider M prime is 0. M equals 1. So answer is 0. That's all. If it is not equal, answer is 0. If it is equal, non-zero matrix element. That's all. This is the rule, second rule. So the answer will be 0. Here the answer will be 0. Because see here, 0 and minus 1. And what is the answer? 0 and 0. So answer exists. Answer exists. We are going to find out. We do not know whether it is 1 or not. We do not know. Okay, we are going to find out. Already we have found out diagonal matrix. Answer is 0. Answer is 0. Here also we have 0, 0. Answer exists. Answer is 0. So for the rest of the matrix easily we have. So we have come to know. So now this matrix element and this matrix element exists, correct? And this is the complex conjugate of this. Look over here. This is just a complex conjugate of this. Your ket 210 is nothing but bra 210. Bra 20 is nothing but ket 0. So just a complex conjugate. 1. Second one is H prime to 1 2 is equal to H prime to 1 because this is Hermitian matrix. There it is equal. Okay, Hermitian matrix. So this is just a complex conjugate. If you solve for this one alone, that's all. Not calculating for all the 16 elements. We need not calculate for all the 16 elements. Very simple one. So this is the beauty of parity. Okay. So we are going to calculate this one alone. Rest of the terms we have rest of them we already calculated. It's nothing but 0. This is just a complex conjugate. And also we said just now this is a Hermitian operator. For all Hermitian operators we will have only real eigenvalues. So this will be real value. So just calculating either this or this. We are going to calculate this. That's all. Again we are going to use, we can use parity method. We will solve, try to solve. See, excited, it's n equals 2. For n equals 2, you will have to remember this formula for the hydrogen atom. For n equals 1, we have already known, correct? So this is for n equals 2. So psi 200, this formula exists, and for psi 210, this formula exists. So first we will calculate 200. This will go for 200, this one. Okay, 200, that is H11 sandwich between ket 200 and bra 20. So as usual, you just pull EF out. Okay, your H prime will be your EF R cos theta, correct? EF is at EF R cos theta. So psi star multiplied by EF R cos theta multiplied by sin theta. And as I said, R cos theta, you can pull it out. It's a multiplicative factor. It's not a operator. So psi star psi will give me psi squared. So this will be your psi squared. Come on. This will be psi squared. So this multiplied by its own. This multiplied by its own. Psi star psi. This is your psi star psi. Multiplied by R cos theta. Then R squared sin theta dr d theta d phi. Okay, in polar coordinates. Is it okay what I am saying? Is it okay? Now, so this multiplied by this will give you 1 by pi. This multiplied by its own factor, that will give you 1 by 2 a naught cube. Then this multiplied by its own, that will give you 1 minus r by 2 a naught whole square. Then this term is this multiplied by its own. So e power minus r divided by 2 a naught. So 2r by 2 a naught you will get. That 2 will cancel. So you will get e power minus r by a naught. Is it clear what I am saying? Come on, I repeat. You have psi star, okay, psi and psi star. So this will be psi star psi d tau. The psi star psi d tau with the Hamiltonian factor. This Hamiltonian is nothing but your EF R cos theta. R cos theta we have pulled out. Okay, so your psi star psi. Psi star psi means 1 by pi to the power 1 by 2 multiplied by 1 by pi to the power 1 by 2. So that will be 1 by pi. So this square term. This is just a squaring. Squaring will give you 2r by 2a naught. So 2 will get cancelled. You have minus r by 2a naught, which is equal to 0. Now what of this one? This is your even parity, and r theta is nothing but odd parity. The total thing will be your even parity. Wave function. Just now we looked into even function. See even parity. Wave function. If it is odd also, if you are going to square, that will be even parity. We discussed. So this will give you even parity. This will be the whole psi star psi square will be even parity. So this will be even odd parity. Integration of odd parity will be 0. So this answer will be 0. Is it okay? You need not integrate. Just use the ideas of parity. You will get the answer. Now you go for the second one. Okay, 200 H210. That is your perturbing Hamiltonian sandwich between 210 and 200. So now you have to use these two. Okay, so as usual we have pulled EF out. So this will be your H prime equal to EF R cos theta. So this will be your psi star and this will be your psi star H psi d tau. Is it okay? Now multiply these two. Multiplying these two. Okay. Multiply these two, that will give you 1 divided by 2 pi. Okay, 1 divided by 2 pi. This a naught, r by a naught, I can pull it out, a naught out. So that will give me 1 divided by 2 pi a naught. Okay, and this term, multiply these two will give me 1 by 2 a naught to the power 3. 1 by 2 a naught to the power 3. Okay, next term will be 1 minus r by 2 a naught. 1 minus r a by 2 a naught. This term. Okay. Is it okay? Yeah, this term. Then e power minus r by 2 a naught multiplied by this one will give me e power minus 2r by 2 a naught. 2 will get cancelled. You will get this. The last term will be your r squared is there. Your r is here. Your r is here. Correct? So that will give me r to the power 4. And cos theta is here. You have one more cos theta and sin theta d theta. So cos square theta, sin theta, dr d theta d phi. Any doubt? So this is nothing but your psi star psi, then h is there, then d tau. Okay. Now, so now we have pulled r term out. R term. This is for the r term. Okay. and this is for theta term. The last one for phi term. You have separated radial part. You have separated radial part. So there must be some integration. There must be some integration. 0 to infinity. Okay, 0 to infinity integration is missing here. 0 to infinity dr. Okay, so this is where radial part. This is missing here, and 0 to pi cos square theta, and this will be d phi. Now the 1 minus integration is here. Don't worry. So integration is here. We have taken only constants out. So integration is here. No worries. Okay, integration is here, and we have taken only constants out. Now just separate 1 minus r by 2a naught, and we can write separately. 1 here minus r by 2a naught here. Okay, 1 here minus r by 2a naught. R, you just put it inside. R to the power 4 multiplied by r, that will give you r to the power 5, and e power this one, and this will be common term, will be e power minus r by a naught. Okay, this r to the power 4 is here. We have pulled 1 here, we have pulled minus r by 2a naught that side. Okay, that side. Now we have already seen this one. This is gamma integral. We have already seen r to the power 4. So gamma integral, gamma phi. Gamma phi equals 4 factorial. Gamma n equals n minus 1 factorial. So you will get a naught to the power 5. Okay, simplify, you will get a naught to the power 5. 4 factorial. Answer will be 25 a naught to the power 5. Already we have seen earlier how to solve this one. And the answer for this one will be 120 divided by 2. There is 1 by 2 a naught. This will be your gamma 6. Gamma 6 will be for 5 factorial. Simplify, you will get 120 divided by 2. So 60 a naught 5. Minus is there, correct? So minus 60 plus 24. That will give me minus 36 a naught to the power 5. Remaining factor is just a substitute. You have EF is here. 1 by 2 pi a naught. 1 by 2 a naught multiplied by, put together, that will give you minus 36 a naught to the power 5. You just try cos square theta sin theta d theta using second method, that is d cos theta. Can you remember? You substitute for sin theta as d cos theta, and you will get exactly 2 by 3, and the answer for this one will be 2 pi. You substitute all the answers, you will get minus 3a naught EF. Minus 3a naught EF. Okay. You have a naught to the power 4. So we will get a naught, correct? Is it okay? Then we can strike it off. So you have 2 2's are here, it will be 8. Then here you have 2. 8 multiplied by 2, that will be 16. Okay. 16 multiplied by 3, that will give you 48. You just strike it off. The 2 pi will cancel. You strike it off, you will get minus 3a naught EF. Is it okay? Any doubt? So the final answer for the expectation value of this one will be minus 3a naught EF. Final answer. So we have calculated this value. We have calculated this value. So which is nothing but minus 3a naught EF. Okay. We have calculated minus 3a naught EF. Now we will substitute minus 3a naught EF. And we said already the complex conjugate of this one will be this answer. So whatever the answer that we are going to have, the same answer will be real one. So here also we have minus 3a naught EF. Here also we will have minus 3a naught EF. The remaining diagonal terms will be the same term. Other terms all will be equal to 0. Is it okay? Now we have 4 by 4 matrix. So we must get 4 roots. Those 4 roots are eigenvalues. Okay, we will have to have. Now we will just take this one as 2 by 2, this one as 2 by 2. We can simplify. Just take this one as 2 by 2 matrix. Just take 2 by 2 matrix and diagonalize, and you will get En squared equal to 3a naught EF whole squared. So En 2. This is for the second exited side. N equals 2, correct? So you have En 2 equal plus or minus 3a naught EF. So two values we have obtained. One is plus 3a naught EF, then another one will be minus 3a naught EF. So we have found out 2. Just take these two matrix, 2 by 2 matrix, you will get 0 0. En squared whole squared will be equal to 0. So that will be 0 0. So we have now 4 values, 0, 0, then plus 3A naught EF, then minus 3A naught EF. So we have obtained 4 values. We will have to add these 4 values to the ground state. That will be the correct energies. Okay. So we should diagonalize this matrix leading to eigenvalues. This one, which is equal to 0, and that will be minus 3A naught EF. Okay. So this is for this wave function, and this is for this wave function, and this is for linear combination of these two wave functions. So both are equal. See? Okay. So we have separate energy. That also we have separate energy. We have the same energy here. This is partially degeneracy. Come on, I repeat, separate energy. So this wave function we have this energy. This wave function we have this energy. For these two wave functions we have the same energy. 0 means it is we'll have to add with a ground state. We'll have to add with a ground state. So this is partially lifted. See, partially degeneracy. Two things are exactly non-degenerate. But this one will have the same energy. So it's called partially degeneracy out of 4. Okay. So what is the conclusion? The conclusion goes like this. So we have 4 roots, 0, 0, minus 3A naught EF plus 3A naught EF. The corresponding perturbed energy values will be. Okay, you have to add with ground state energy, which is nothing but minus 13.6 divided by 4 n square plus 3A naught EF. Then other thing will be 0 plus 0, correct? So minus 13.6 divided by 4 plus 0. So this value and this value. And here you will have minus 13.6 divided by 4 minus 3A naught EF. So all the 4 energies. Look at these two energies, they are the same. These two energies are different. They are different. So out of all 4 energies, 2 energies are the same. Okay. Again they are degenerate. So they have degenerate values. The corresponding state functions are. So this is for the first one, and this is for the second one, third one, and fourth one. So they are the linear combination. So this will be the highest level, and that will be the lowest level. Corresponding wave functions, state functions are. This perturbation has only partially removed the degeneracy of n equals 2 level. E2 and E3 still have the same energy. So we consider this as 1, so this will be your E1, and that will be your E2. Last one will be E2, and remaining these two will be your E3 and E2 and E3. That will be your E4, and E2 and E3 are the same. They are different. E1 and E4 are different, whereas E2 and E3 are same. So partially degeneracy. The states 2, 0, 0 and 2, 1, 0 are affected by electric field, whereas these two states are not affected by the electric field. Thus the 4-fold degenerates is lifted partially. The energy level is raised by 3A naught F for one wave function and is lowered by another wave function. Okay, one is plus 3A naught F, another one is minus 3A naught F. So one is lowered, another one is raised. For the remaining two wave functions, the energy levels are the same. Okay, so this is the whole picture about the splitting of energy levels in the presence of electric field. So we have started with, can you remember, n equals 2. We are going to apply the electric field now. So the split has been taken place like this. One is up, another one is low. So up level has En0 plus 3A naught EF. The down will have En0 minus 3A naught EF. And they are separated equally. See, they are separated equally. One is plus, another one is minus. Separation is equal. What is the wave function? Look at the wave function, and this will have the linear combination, and this also will have linear combination, and this one will have the separate wave function. That this will have the same energy. So this also say, see, this is for each wave function will have each energy, but this one will have the same energy. For two different wave functions we have the same energy. So that's why we say that this is partially degeneracy. Okay, these two wave functions have the same energy. So further it is known that when an electric dipole is placed in an electric field, so this is the conclusion. The change in energy value is given by minus P dot E. Okay, the change in energy. So that is the interaction energy, dipole moment energy. So it suggests that the hydrogen atom in n equals to the first excited state behaves like an electric dipole moment, the value will be 3e a naught. Okay, so dipole moment. The dipole in electric field gets itself oriented in three different ways. One will be one state parallel to the electric field, another one will be anti-parallel to the electric field, then two states will be perpendicular to the field. So we have four states, correct? We have four states. So one state will be parallel to the electric field, another will be anti-parallel, then those two states will be perpendicular to the field. These two states, they don't possess dipole moments and they don't have first order interaction with the field. Okay? Any doubt? So we'll stop today, and this is about Stark effect. Very important question. Okay, bye students.